Я can't check, but we're on air. Как? Слышно? Доска видна, да? Доска видна. Yeah, so today we shall discuss Dirichlet theorem on units. Сейчас, секунду. Я все испортил. Yeah, so today we shall discuss Dirichlet theorem on units. But before we have to say some remarks, so just yeah, so as usual, so we have k is the extension of integers. So and here you have the ring Z and the integer, the ring of integers O of k. So that's the ring of integers over Z. Yeah? And also, yes, we consider the finite extension, so k over q is less than infinity. Yeah, and we have the following, so we have yeah, so the task which solves the Dirichlet theorem on units is to describe, so aim to describe the group of units in of k, so meaning that they are just invertible elements. Yes, so the group of invertible elements. Of course, just invertible. Of course, you consider just non-zero elements, of k, and you look at those elements that are invertible. So let us recall that, so something about valuation. So suppose you have P, now you have some prime ideals, so some prime ideal, and this allows you to consider localization of O of k with respect to P. So this is so it's also in k. Yeah. So this is localization in a multiplicative set of k without P. And you have this set, and so inside this set you have the ideal obtained by localizing P. So just here was the ideal corresponding to P. Yeah, so this is actually ideal that is. So you have to consider the ideal and generate the ideal in the larger ring. So this under our assumption, that this is integrally closed, closed ring. So this is the Dedekind domain. And when you localize, you remain the same. So this is principal ideal. So this is, we have proved that when this ring is local, so when we have local integrally closed ring, with dimension of all KFP is equal to 1, so any non-zero prime ideal is maximum. Yeah, so in this case you have so this is generated by one element. So this is principal ideal domain. As we have proved, yes, actually we have proved that prime ideal is equal to ideal generated by one element, and this implies that I is just a power of some prime ideal. There is only one prime ideal in this local ring because there is only one maximal ideal except 0, yeah? And this means that this is just pi in the power n, so this is principal ideal. Yeah, so also, so this allows us to introduce relation. So if you take x, so that belongs to the field K. Yeah, so it is, you may just consider, so K is a fraction field of O of K, so you may assume that you belong to O of K. And your x ideal becomes just e to the power n, and this is p to the power n for some this fixed p. Actually, p belongs to, as we have noticed, p without p square. And x can be written as unit times, so this means that x can be written as unit times p to the power n, and this way is unique. So this is a unique way to write it. And this implies that, yeah, so you can consider the so-called valuations. Yeah, so that's what called valuations. So valuation actually is this power of n. So the valuation that is associated to x is precisely the power of n that is used in this way to write it down. So this is p and this is unit, yeah? Unit element. Yeah, so notice that it is in O of kp, so not in the whole ring. Yeah, so just you consider it, so you consider it as a subset in this localization, and you can proceed with this. This allows you to describe relations, so just O of k maps to R. So this is called relation. Yeah, so if you have the following, so first of all, you have nu of x plus y is less or equal than nu of x plus nu of y. And the second is a multiplicative property, nu of x, y is equal to nu of x times nu of y. So there are several ways, to define relations. So you can use multiplicative form or additive. So here let us use multiplicative form of relation. And if you use this form, so notice that if you speak about relations, so non-Archimedean relations, so they come with the following property. Instead of 1, you are saying that nu of x plus y is less or equal than maximum of the corresponding relations. Yeah, so if you notice that if you use 1 tilde, then you can consider the following subsets. So in this case, you can easily reconstruct prime ideals. Yeah. So this in this case, the ideal P can be defined as the set of X inside K with nu of X less or equal than 1. Notice that if you have two numbers, so the sum is still less or equal than 1. And if you are speaking about strictly less than 1. So if you are speaking about of Kp, yeah, so that is written as x belongs to K, such that nu of x is less or equal than 1. And one proves that, this is why actually we are speaking about this type of relations. So if you think of corresponding topology from the viewpoint of topology of Kp is compact set, it is bounded and closed set. Yeah, so also actually P will be a closed subset, but this will be just seen a little bit later. So notice that if you have relation, then P is maximum. The ideal is defined, and you also the relation that is constructed before is really obtained this way. So the relation of x that is used as u times p to the power n and nu of x is just so here one should define it, the relation as 1 over p to the power n in order to have so multiplicative property is evident, but in order to have this maximum, so this relation is less or equal than this maximum of relations. So then you should have the relation equal to on x equal to 1 over p to the power n. This is in order. So notice that if you are looking at 1 over p over n, yes, so plus 1 over p over m. Yes, so you are using the power of just smaller power of a larger power of p, so suppose n is bigger or equal than m, then you may write down, so u1, so u2 here, then you may write it down as 1 over p to the power n, so u1 here, and u2. Yeah, so you are writing down that u1 plus u2 times p to the power n minus m, and this allows you to see that, so the relation of this thing, if you think of it, yeah, so it is still, if n is bigger or equal than m, then this is still unit, yeah? So that implies that relation of this sum is 1 over p to the power n. Or you can, it may happen that n is, at any case, so this is the element of O of k, where the relation is bounded by 1, less or equal than 1. So this implies that you are just saying about the product, and the product is smaller than maximum. Yeah, so smaller than this maximal relation, if you think of from this point of view, 1 over p to the power n. I mean, of course, yeah, actually, this is not, yeah, so this is, I mean, this doesn't, so if you're speaking about so this makes sense, of course, when the way we are defining this relation, so this makes sense for number field, so makes sense for number fields. Yeah, so when you are thinking when p is just obtained from the prime number, I mean over q, and if you want to but if you think of the relation in more general setting, yeah, so then of course you should do the following. So instead of this notation, yeah, so you so you should have a logarithmic notation instead. I mean, you should keep track on the powers. And if you want to define this for number fields, yeah, so for relation for number fields, I mean, the problem is that this relation for not number fields, yeah, so it takes values in k, yeah, so in the field big K, and form there some subgroup, yeah, so this form discrete subgroup, so form discrete subgroup isomorphic to Z, yeah, by associating the power. And actually, when you're speaking about relations, so that is it maps to the group with the order where you can compare numbers. Yeah, so that it maps to the group G, which is, for example, if you're thinking about discrete relation, then you're mapping to the group G, and the group G is isomorphic to Z. Yeah, so when I just I use 1. So in this case, G is equal to Z. So G is the group where the relation takes values, it is isomorphic to z, and this is the way to write it down. And actually, if you want to write down the evaluation for arbitrary, if you want to think about the evaluation of for the number q, so the p plays role of the p, and so this is prime number. So okay, you can put equal to b. So first way to write it down is O of k equal to q. And this then p is just some prime number, and the x is written as plus minus 1 p to the power n times unit in the local ring. So you are taking the ring of q. So you are taking z and you localize by p. Yeah. So you localize by z without p, yeah. And the localization by p means that in this set all elements that are not divisible by p becomes invertible, and this is precisely so you can write down any integer numbers by u, the number that is doesn't contain p, as divisors, and p to the power n. So that means that valuation of x is just taken to be 1 over p is defined 1 over p to the power n.
So okay is z.
Okay is q.
Yeah. Okay.
In this case, yeah. So this one can try to extend the valuations. Yeah.
Yeah. Okay, the integral closure.
What?
Okay, the integral closure. I mean.
Oh, I mean k is equal to k is z. Yeah.
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 Here you k is q.
Yeah. K is equal to q.
Okay.
So actually, there is a way to define the group of relations by this formula as a subgroup of k, or by this one. And if you are thinking about Archimedean relations, so Archimedean of Q of K, they come from the following construction. So so you apply, so you have embedding of K inside algebraic closure of Q. So this is sigma, and algebraic closure of Q, so that you can consider it as a subset of C. Yeah, so you just choose. So algebraic closure of Q, of course, it is the ring that is corresponds to the irreducible polynomial with coefficients in Q. Yeah, but you can put them inside the ring of complex numbers where you have a well-defined norm. Yeah, so you have the map to the R, which is maps Z to Z times conjugate, and you take the square. And so you may consider the mapping. Yeah, so the element psi here maps to sigma of psi, and you may take the norm corresponding to this operation. So this describes all Archimedean relations, and this is what we have described. So this description of relations It is called the Ostrovsky theme. Yeah, so we omit the proof. Yeah, so notice that there is a way to, easy way, as we have noticed, it is easy way to understand how to associate the prime ideal to the valuation. So given a valuation, of course it is clear that if the valuation is general valuation, but is Archimedean, yeah, so that is that doesn't satisfy some strict, so that inequality which is stronger, then you cannot take the so you cannot find the ideal, and this defines via this kind of operation. But if you already have valuation that is non-Archimedean valuation, then of course so that two things gives you precisely the ideal, because it is easy to check that this is, so first this is a ring, yeah, because the product is evident, and the second condition of that you have inequality, it is really, so the sum is less or equal than maximum, then still the sum of two elements has the valuation less than 1, less or equal than 1, and the same, so for this is maximal ideal. It is not very hard to prove. And this, if you want to also if you want to extend valuations, so if we want to, so extension of relations. Yeah, so already this so if you think of extension of relations, then you think of the following procedure. So you take prime ideal P, so corresponding to some prime number, actually, and you extend it, so this is ideal in. So the extension of relation is general procedure. So this is, suppose you have extension of rings, so K and L. So you have the corresponding fraction fields, and you have the following. So you have so here you have prime ideal P, and here you have ideal beta lying over P. So beta is lying over P. And this implies that beta intersection with B is equal to A. And if you are speaking about if P is already discrete valuation ring, so I mean we can localize
equal to P.
Oh yeah, sure. Thanks. So if you localize B by the corresponding multiplicative set, and we localize A by the corresponding and the B and the 8 by the corresponding multiplicative set, Yeah, so this we will have that. We will have this kind of equality, and of course, this localization of A will be a subset of localization of B by this thing, and so note that. So this is S. So note that. Yeah, so that A localization by B is just the subset of B localization by beta. And then we can consider P, instead of P, we can consider P AP. This will be ideal line over beta. So, so beta, beta lie over this ideal, and you can just do the following. So you can take P and you can write down P times beta B, and this will be beta in some power, and this is precisely ramification index. Yes, so that just you see that there is only one ideal. So B beta is a local ring, and beta is the only maximal ideal there. So knowing that A is there, so if you have A is dedicant domain, L over K is finite, and B is finite. B is integer closure of A. In L. Yeah, so this implies that you have ideal that so B beta is some power, and also we know that this is equal to omega in the power E. Yeah. So for uniformizer, so omega is ideal. So beta is just generated by omega. So this is uniformizer of B beta. And notice that P times P beta, yes, so you have, we have a uniformizer which is pi, so corresponding uniformizer. So this generating element is called uniformizer. So you see that this ideal is just pi over, so pi times P beta. So this means that up to just from this point of view, omega is just pi is equal to omega E. Yeah, so from this kind of ideals. So if you want to, so the idea is to define, so of course, when you are thinking about logarithmic way to define valuation, so the valuation for this A is just, so is written in terms of P, yeah, so uniformizer, and the valuation for B is written in terms of omega, yeah? But of course the elements of A itself, yeah, so they can be viewed as an elements of B. And from the viewpoint, so this means, so for example, as we can see here, yeah, so the elements, if you consider the valuation from the viewpoint of the ring A, it should be 1. From the viewpoint of the ring B, it should be E, yeah, of the same element. So this tells you that one should define a valuation, so define valuation of B yeah, so of omega by putting so precisely taking the corresponding root from P. Yeah? So by putting just the root of the power of E of 1 over P. And this, I mean, when you are thinking about when A is a ring of integers, so when A is the ring of integers, so this implies that this relation is just 1 over P, so you are extracting this 1 over E here. Yeah. So, okay. So let us consider the corresponding formula, which is called projection formula, product formula. So product formula. And the product formula for Q tells us the following. This is tautology for tautological statement for Q, but quite important because so notice that any element is written in terms of plus minus. Yeah, so P1 in the degree n1, etc. Pk in the degree nk. Yeah? So when you want to calculate you may so what is description of valuation? So you have valuation corresponds to new valuation that corresponds to P. So prime number, and the infinite valuation just module of the number. Yeah, so this is called the infinite valuation, and this is denoted by valuation of infinity, and this can be denoted by valuation in P. And if you are thinking about valuation in P, yes, so that you take, let us take the product of X over all possible valuations over P. So P belongs to spectrum of Z, and times infinite valuations, so times valuation at infinity. And the answer is more or less tautological, so you have to, and this really tells us why we're choosing. So of course, if you're thinking about group of valuations, this is group isomorphic to Z, you can just make a choice for quite different choices for the valuations, and it is not so important how they look like. For example, you can use logarithmic notation. Yeah, so just you have to, I mean, you change the definition of valuation, but you just use only the power of the corresponding element. Yeah, so instead of optional way to define it, so optional way. To define valuations is logarithmic notation, so optional to define valuations in in logarithmic notation. Which is just n. Yes, so the valuation of x is just n, and it of course it will satisfy a little bit different inequalities. Yes, so that it will satisfy, instead of the product, it will satisfy the sum, and this instead of this, so the maximum it still will be, well, it will satisfy minimum actually, yes, so that, so if you just, so this is just, so in logarithmic notation, this will be omega of x, y is just omega of x plus nu of y. Yeah, and here you will have, yes, a logarithm is just monotonic function. Yeah, and so if you take logarithm, so here we say that if you are speaking about valuations, so if you just put n to be pi of n, so the valuation of pi of n is equal to n, then of course if you write down p to the power n plus p to the power m, yeah, so you can write it down like what you can write it down like minimum of pi, yeah, so pi to the power n, and times unit times 1 plus pi to the power n m minus n, yeah, so that will be and of course it can happen that these guys cancel if there are, I mean, if you have more complicated way to write down as the sum of pi's and the units. So this will be larger, so this equality is larger or equal than minimum of nu of x, nu of y in logarithmic notation. So, so for logarithmic notation. And this yeah, so this yeah, and this explain. I mean, in when you are, for example, working in functional fields like the fields, so the extensions of polynomials, so it is convenient to use this logarithmic notation. If you are using number fields, so this is more convenient to use the definition of valuation that I have given, since this product will be just in our case 1 over p1 and 1, just by definition 1 over p2 and 2, etc. 1 over p k and k. And for taking the infinite norm, so this I wanted to write down infinity. So here I'm writing down this p1 and 1, etc. pk and k. Yeah, so I'm putting plus sign, and the product is evidently is equal to 1. So if you're thinking about the same thing as for uniformizers, so you can think of the following product formula. So what one should do in order to write down the corresponding product formula, so you can define the norm. I mean, if you are defining extensions, so this is spectrum of A, this is spectrum of B. So here it is O of K, spectrum of K, and this is just this will be spectrum of Q in our example. So you can do the following. So notice that the norm is multiplicative. This valuation is multiplicative thing. So you can define valuation here. So valuation corresponding to beta. So if you think of P, so you can think of the following. So you can think of so you can take just the product. So take the product. The product of norm. So you can introduce actually norm in terms of here you can here you can do the following. So here you can think of the following. So here you can consider the norm. So you can take the product of mu P. So if you have the if you have the element of beta B inside the B, so the ring that is lying over A. So you can consider the product. So you can take the norm of K over Q of this element of beta, and you can take a product over all prime numbers P. So you can take mu P of the corresponding norm K over Q of B. And in the same time, you can take a product at infinity, so that will be the norm of K over Q over B. And this is equal to 1 just because the norm is an element of A where the product is 1. So A is equal to Z. So we just apply this formula for Z. Then we can open the definition what is norm, and so you can write down what is this kind of relation. And this is just a product, the norm is just a product of all sigma B over all sigma that embeds K into Q bar, and this embeds in the complex numbers. And here, So you are taking the absolute norm here, so in the complex numbers, and this the product is itself by definition. So these guys are just that are called. This is a way to define a set of. This corresponds to the set of Archimedean relations. Set of Archimedean relations. Yeah, and this just if you think of think of the other just part. Yeah, so then you have the following. So you have we can define norm of P. So we can define, as we have discussed, the norm of ideals. So here we can define a norm of ideals. And here you write down the ideal. So the norm of ideal is equal to the norm of element. Yeah? So this from the viewpoint of norm of ideal, it is precisely norm so the number of elements in the corresponding quotient. Yes, so norm of, let us recall that we have defined norm of ideal A, and it was so norm of A was equal to the number of elements in O of K modular this ideal A. And notice that we have proved that for elements these norms are the same. Yes, so for n of B over K mod Q. So the norm of this thing of the elements is the same of taking norm of the element and taking the corresponding ideal generated by this norm. And this means that you just from the viewpoint of P, when you are taking the corresponding evaluation, yes, so the the element B can be written. So just if you consider the ideal P and the ideals lying over it, so beta 1, etc., beta L. So ideals lying over P. Yeah, so if you take arbitrary element beta, so you will have, it will be written as the product of the following, so it will be written as the product of the elements G1, etc., beta L, GL, and times, so notice that this equality is sufficient to check when you localize by, so since both of them are ideals of the decomposition, in order to keep track what is connected with B1, BL, so we can take, so can localize in P, localize in P to keep track track of ideals lying over P. And from the viewpoint of decomposition, you take actually arbitrary decomposition. I mean, in all of the ideals that are possible. Yes, so that. Yeah.
You said the norm of ideal is ideal, and why here you write norm A is just
Norm of yeah. So when you want to map it, so norm of ideal, is just I mean, if you want to map it to the so here I mean your question is but notice that this is actually the number. So this is norm of the element is integer number. And you generate the ideal by this number, so you can recover the number.
So the norm A is also ideal generated by this.
I mean from from the viewpoint of ideals, this is principal ideal generated by this. And in more general setting, this is of course the product of corresponding ideals. Yes, so notice that norm of beta. So as we have defined, norm of beta was P in the corresponding ramification index. Yes, so it was P in inertia index of beta. So this, but in this case, you are just you have the equality for numbers, and this implies that norm of so if you want to write down norm of psi, so norm of psi itself, it is just norm of psi. It is just the number of elements. So the ideal generated by the number of elements of k, psi of k, and this is a product of its so that was norm of b. I want to say. So norm of b is just this ring, and the b is decomposed into the coprime parts. So I mean you have the following. So if you have ideals lying over, so you have ideal P1, P2, etc. And you have the corresponding blocks of ideals of beta. Yes, so P beta 1, 1, P 1, 2, etc. And here you have beta 1 over P 2, 1, beta 2, 2, etc. And you have this pk and the corresponding blocks of ideals. So when you are thinking, so when you take a B and you decompose it into the product of ideals, so you can take this, so notice that B's itself are coprime, so I mean all of them are coprime to each other. So from the viewpoint of this ring, this is just a product of all of k modular b I in the power, so b I in the power gi. And you can take, I mean, if you are thinking about, so when you are taking the corresponding valuation, so this is a product over I plus, so this is part, you can decompose it. So this product into two parts, yes, so we can decompose it into the product of part where you take the product of beta line over k, so over p, so this beta I intersection with z is just this p, and just terms of k over beta tilde I j, I mean, so different things, j tilde I, yeah, so just this beta I tilde so intersection with z is just some number, q is prime to p. And so when you are taking the evaluation corresponding to p, so you take into account only the product of ideals lying over p. Yeah, so when you are thinking about n of beta, n of b, and taking the evaluation with respect to p, so you can keep track only of the corresponding valuations. So this is a product, so this is taking the valuation over the product of the part corresponding to p. So this is, you can rewrite it, since you have a uniformizer as a power of the number of elements in B, and this, when you take it mod P, so this is precisely the product, so taking the norm of the product of P, where you, this thing, taking the number of elements, this is P in ramification index, in inertia index, and then you raise it to the corresponding power, so this is just writing down GX. So this means that if you decompose this formula separately by, yeah, and you are taking the norm of P, that's saying that you take 1 over this number, yeah? So when you are thinking about the corresponding norm of beta, so you can write it down as the product, so the product of norms over P in spectrum of Z, so the norm of K over Q over psi over B can be written as just if you take the product over infinity also, so infinity means you are thinking about sigma i's that embeds k into c. Yes, so you are thinking about new the norms. So here you are taking the corresponding norms with respect to p, and here you are taking the corresponding norms with respect to sigma of p, yeah? And taking absolute value, yeah. So and this. So this is by projection formula is equal to 1, and we have rewritten these parts. So the norm of P can be written as follows, and notice that this is precisely norm of corresponding ideal beta, and you can think of this number written in terms of corresponding norms. So if you calculate the norm of ideal beta I, then of beta, so then it should be raised. So this norm is smaller. In order to obtain p, you have to raise it into the corresponding ramification index. So this is how we decided to consider it. And then you can write it down f1, and you take the product over, so beta I lying over. So you take a product over all p in the spectrum of Z, and you are decomposing it over all beta i's that lying over p. And so this for each beta I you have this kind of index, and you have this just the product of infinite valuations. Yes, so just sigma is the corresponding valuation at infinity, and this product is 1. So this is called a product formula. Yeah, so and what is the reason that you can write down? So if you have psi, if you have b, so you write it down. So that is precisely what we have done rewriting this formula. Yes, so for each factor we have written it separately, and this allows us to you think of the norm of beta I, of course, in terms of uniformizer. Yeah, so you are thinking about uniformizer, but it is raised into the corresponding power of ramification index, and then this gives you integer numbers. So notice that if you take b is just some power of corresponding J1 of the uniformizer, and but if you take valuation corresponding to beta I, we have just described it as 1 over uniformizer. Yes, so it will be 1 over uniformizer G1, and when you raise it to the power EI, that will be P. Yes, so that so since omega lie over P, so omega in the corresponding power EI is precisely the ideal P. So this in this notation, this factor will be actually already. So this factor is the integer number. Yeah. So you can use either the notation that is consistent with all extensions. So you divide it by the corresponding EI, the corresponding valuations. Or since it is more convenient, you just consider them. You can consider the corresponding extensions, and you keep track. So that will say that even if you extend the value of our p, yes, so the value of the norm on p will be the same. So this is quite convenient here, but we pay price so that this is not integer number, but anyway, in the product formula you write down it in a way that it will become integer. And this, yes, so you can write down that this is just p corresponding to b. And you raise it to the power of the corresponding ramification index, yeah, or corresponding inertia index. But what you have to notice that this is a product, or so you have the function on norm corresponding to different prime numbers, and the product, so you apply some function on them, like raising to the power, and then you take a product and it is equal to 1. So this means that, for example, if all the numbers except 1 are sufficiently small, then the last number is sufficiently big, and vice versa. And that we will use it after the break. So let us make 15 minutes break.
На 300, вроде 300. 100 рублей в месяц. Можно просто один раз человек купить. Ти показує, коли слідчого Какие же концерты. Левин посмотрели возможно? Вы его видели?
У меня запись.
Но единственное, да,
Еще пусть.
да. Нет, пусть это подальше. Не важно. Важно, отлично, так вот. Это навигация в сторону. Условия? А, точки, я тебе пишу вот так. Ну, точка А, например. Да, так. Ну, в смысле, кстати, слово точка. А, да, это замечательно. Я не люблю.
А вы чё?
Нет. Ну, мы не хотели Левина, но добились. Вот это. А мы с Катей болтали с ним.
Вы Левина?
Нет. А что с Левином?
Но меня проводила подруга, мы бесконечно на метро. Я проводила подругу, и потом ей срочно пора было закрашать. Я думала, что
Okay, let's just continue. So now we are ready. So what is important for this formula that you have the product over infinite relations and finite elements of spectrum of D, of course, so up to some finite numbers. And of course, if you define relation of beta as the corresponding norm of ideal, then just if you think of, so if we define as the norm in beta I as the number of elements in the corresponding ideal, so that in the localization that will be precisely p in this number, so p in EI. So as the number of elements in the just you take localization in beta I and you take it modular the corresponding ideal B. Then this will be just this will be this norm of beta in the power EI precisely. So that will be the 1 over, I mean 1 over node, so it will be 1 over p in the corresponding degree G1. And this, so this will help us to study units, since you have the following map. So you can consider the following. So let us recall that we have just two types of embeddings. So complex embeddings and real embeddings. R is real embeddings. And this is complex embeddings, meaning that K, our field K, embeds into C, and here it factors through R, so that actually this is the embedding in R, and here we're speaking about embedding in C, in the corresponding complex numbers. And you can think of, given an element, you may take the corresponding sigma 1, etc., sigma n, where you just use only a real, you have actually two as complex embeddings, but they each, so they come in pairs, they differ by complex conjugation. Yes, so that here the embedding sigma comes with complex conjugate. And this implies that so you can map outside, take the corresponding norms, and take logarithms. And notice that they will, so what you know for just for the formula, so what is unit? Unit means, so size unit. So this implies that in each P it should be invertible. I mean, when you take psi modular corresponding beta I, where beta I is ideal, length over some pi is invertible element. So so this means that so it is invertible element in O of k. So that means this is invertible in localization in O of k beta I, and this will imply that omega beta of psi is just equal to 1, it is unit. Yeah. So I mean the corresponding, if you think of multiplicative norm of invertible element, it is just so if you have a uniformizer, you put 1 over p to the power n, n is equal to 0 here, so it is just unit element. And so psi is unit in O of k, then it implies that its norm is equal to 1. And actually vice versa. So if you have the element and each norm is equal to 1, then the element is invertible. Since actually you can look at the ideal corresponding to psi and decompose it in the product of beta i's. Yeah, so you can think of ideal psi, decompose it into the product of beta i's. And you may think of this. So you are decomposing it into the product of beta i's, and this implies that if psi is invertible, then this ideal is trivial. So all j's are equal to 1. So to 0. Yeah. So if psi is invertible. So if and only if all j1 etc. ji is equal to 0. And then you take psi, you map it to the logarithm, you put it like this, and these are only infinite extensions. So you see that you have a projection product formula. So by product formula, so you have the product corresponding to sigma to nu beta of psi in the power ei phi. Yeah, so I can write it down in order so that I shall put on the phi in order to emphasize that I'm writing down the integer numbers times the product of infinite extensions. So sigma belongs to so sigma embeds again k into c. The product is over norms of sigma of psi. So this is equal to 1. And this gives you the formula. So when you're speaking about the units, so these guys are equal to 1. All of them are equal to 1. And the remaining part is just the sum of elements equal to 1. So if you think of logarithm, so if you take a logarithm of this product, then this is equal to 0. So for the image, so notice that you have complex, so here you have real relations and complex relations, and here in the formula for norms they come in pairs, so you have some of the coordinates with coefficient 1 and some of the coordinates of coefficient 2. But anyway, so this is hyperplane. So this means that this, from the viewpoint of logarithm, this is a sum of a logarithm of the norms. Where sigma runs over k inside C, and this is hyperplane in. So this is hyperplane. I mean, if you consider this as a coordinates, so this is as a coordinate functions. So hyperplane in R plus S dimensional space. So units a priori, so the map is here that we have considered the sum of logarithms is of course inside R. So notice that so we're taking the embeddings in the complex space. We take the norm, so we take real number and take the corresponding logarithm. So this will belong to R plus S, and this, but the image actually is smaller. It belongs to this hyperplane, and so the group is so notice that the group is discrete there, so note that image of if you think of I, so you can consider the map of the whole ring of K, so which is actually larger. Yes, so you can take yes, so let us call it I, the map I. So I. Ring I. So notice that the group so of K maps discretely. So it is so maps as discrete set. Since I mean at least 0 has a neighborhood that is distinct from different other points. Yes, so 0 has a neighborhood distinct from other points. I mean just so has neighborhood. Sorry. So it has neighborhood that doesn't contain other points. Yeah? So it has neighborhood that does not contain other points. Yeah, so since you, yeah, so of course some of, yeah, because you, if you think of the product, yeah, so that yeah, so here we think of the just this before. So we discuss the thing before logarithmic map. So before taking logarithm, you see that if you take the products of the corresponding betas, so of then you know that the values of valuations are less or equal than 1. And if you yeah, and this yeah, so actually, so if you think of so the 0 doesn't contain the neighborhood, since you have so this product, so you cannot have sigma i's, sigma of x, so can be made cannot be made too small. Yes, so that sigma belongs to k, that cannot be made too small in comparison. I mean, if this number is small, and by definition the norms of the different factors are less or equal than 1, so this product cannot be 1. Yes, so that 0 doesn't contain the points of this set. So this and also notice that I mean, if you just consider the points which are yeah, so also notice that the product is 1 over p. Yeah, so if your elements are I mean that the points they sit discretely in the space. Yeah, so if you have your if you have the yeah, so I just wanted to say something about the 0 here. So okay, so let us consider. So let us recall the following, that yeah, so let us recall the definition that if you have gamma, so if you have gamma inside V, so it is called it is so V is a vector space. So we start with a vector space. So V is a the vector space. So here we think it over R. Yeah. So we consider the group inside V, which is it is a Billion group which is finitely generated over Z. So finitely generated group over Z. And the claim is that this, so the theorem that I want to say it is very easy. So this group is finitely generated if and only if this gamma is discrete. Yeah, so discrete means that any 2 points has neighborhoods that can be separated by discrete means that either, so you have several notions of discrete group. So let me recall it. So what is gamma is discrete? If you have the following, so if you have the neighborhoods of 0, so bounded neighborhood, contains finite number of points, like this. So if it is so, you can take sufficiently small neighborhood, so there exists a neighborhood of zeros, so neighborhood of 0 that doesn't contain other points except 0, so open neighborhood of 0 that does not contain any points except 0. Yes, so meaning that you have 0 here and all points are outside of your group, or you just can, so any point satisfies of the group satisfies this property. Yeah? So equivalently, so any point of group satisfies this property, yeah? Because you have translations by your group. So any point of such group satisfies this property. And if if the group is finitely generated, it is discrete, and moreover, it is generated. So you have a fixed basis. So and gamma is equal to z e1 plus etc. plus z en ek for linearly independent vectors. And k, of course, is less or equal than dimension of E. Yeah? So this means that the group is very specific. Yeah? So if it is discrete, I mean, for example, in Q, of course, you may take two elements, start generating the group. So you have option that it is either isomorphic to Z or the elements are not commeasurable, and they generate the group which has near zero. It has dense set of points, yeah? So that are in the neighborhoods of zero. So this theorem I won't prove. This is more or less straightforward, actually. So the idea is to take the box, and you to each element you can associate I mean, you can decompose the basis. So if you have the set of generators, so you can decompose the basis into the first part of the basis and the remaining, and you can put everything in the box, meaning that you just use the fractional parts and of the coordinates, and this will result into that the group. I mean, it is direct to prove that it will have dense near zero there will be infinite number of points. Yeah. So the question is that when discrete group is a full rank. So the question is that question when discrete group is of full rank. This will be precisely so the criterion is about so that it is what we are going to apply to the ring of integer to the image of the group of units, and the criterion is very easy here. So just so we have the following criteria. It is the following. So gamma inside V is discrete group. Yes, so then gamma the tensor R over Z is equal to V. This is precisely saying that the group is of full rank. Yes, so that this element, so that we have description of the is the full basis. If and only if there exists a bounded. Yeah, so F V is of course finite dimensional set. I forgot finite dimensional vector space. So if there exists a bounded set X such that gamma plus X have a whole space V, when gamma runs through translations. Yeah, so when gamma runs through all elements of gamma. So the union meaning just yeah. So for so meaning that so where gamma runs through all elements of the group. Elements of the group. Yeah, so meaning that so that V is just the union of gamma plus X when gamma runs through all elements of gamma. Yeah, so and of course, so let me show geometric interpretation of this, and this is so if it doesn't cover, yeah, so if it doesn't cover, you see the situation like this. So you have so the sets are open. So the X are bounded sets inside inside the V. So the picture looks like this. So you have the space V here. Okay. So you have the group, the span of gamma times R over Z. And you take simply, so you have the points of gamma here. Yeah, so you have the corresponding points. And you have some bounded set which is just translated by gamma. Yeah? So like imagine that you have a proper subspace, for example hyperplane, and you have spheres, and you start translating spheres. And of course, I mean, if your translation is in this hyperplane, you won't cover the whole V. Yeah? So, and if you cover the whole V, then so the question is to prove that non-trivial part is to prove that if your set if gamma contains in the proper subspace, then the union of such balls cannot cover the whole yeah, so and this is done as follows. So you pick up 0 here, and you take the vector. Yeah, so here I denote the vector so that this is a vector space V0, which is gamma times R. And so you take vector V, and you will take, we shall take n times vector V, where n will tend to infinity. And idea is that even if V itself is covered by the ball when you go to infinity, so if the vector is outside of V0, so that when you go to infinity, then of course it won't be covered. And let me just do the formal proof. So proof that if V0 is not the whole space, then we shall find vector which is not covered. undefined vector not covered by translations, gamma plus x. And this will be, so we take V that is not inside V0, so take, and take n times V, as we shall write down xn, where it is an element from x, yeah? Plus the element of gamma. And of course, yeah, so you just, this is a bounded set. So this means that V itself is equal to xn to the limit. Yes, so when n tends to infinity, where you take xn divided by n plus limit when n tends to infinity, gamma n divided by n. And gamma n is inside gamma, so it is inside V0, yeah? And xn divided by n is in the bounded set. Yes, so since xn in the bounded set, so this is bounded set. This implies that limit xn divided by n tends to 0. Yeah? So this implies that V is just is a limit of the vector gamma n divided by n, but gamma is inside V0. So this means that this vector tends to 0, and this is an element of V0. So this means that this element is the element inside V0. That is contradiction. So that contradicts the assumption. So this contradicts the assumption. Yeah, but you see that, I mean, so geometric picture is quite clear, but the proof is even easier than drawing geometric picture. So, so in order to now to how we shall apply this theorem, so we shall notice that we have we have the image of O of k inside your space under this map I that we have described, and we have the corresponding group. Yes, and notice that here gamma is it doesn't even we shouldn't even know that it is discrete. I mean, in this proposition, we just used that it is a group of translations. Yeah. So also, yeah. So what we have to notice that so we want to prove that gamma is of the full rank, and notice that so here you have the image of integer numbers, and we shall prove that yeah, and also we have the map of just we shall prove, we see that we shall also, we also have this kind of map, so we also have that just embedding even before taking, so the embedding of k before taking logarithm is linear, yeah, so it is sigma 1, so an element xi, yeah, so maps to sigma 1 of xi before taking norm, sigma r plus, map in the corresponding vector space. So let us first, and then we're taking the corresponding norms, and then we're taking logarithms. So first claim is that so it may be a little bit strange claim, but we shall need the following lemma that will allow us to choose the corresponding sets, the corresponding bounded. Yes, so now aim is to construct, so in order to prove that the group O star in the corresponding logarithmic map is of maximal rank, we have to construct, we have also OK star, so units, the group of units that maps to corresponding logarithms. Yeah, so actually here I would say that so here we map to 2s. Yes, so you have to use the map and the conjugate, the degree of the extension of k over q, and we know that so under this map of k is just it is a group isomorphic to the z to the power n, and it is of full rank here. So here it is full rank. But then you just use the corresponding projection to only keeping the factors with remaining taking only the subgroup of units, then it will be the subset in the hyperplane. So the image lies in the hyperplane. So image lies in the hyperplane. The sum now. Which is isomorphic to R plus S minus 1 hyperplane. So consider alpha inside of K, so such that the norm of K over Q of alpha is equal to A. Yeah, so where you fix, so where A is some fixed integer. So I claim that then the set of such alpha, so then the set of such alpha is finite up to taking a product by the units. So up product with psi that belongs to O of star of k. So this means that if you have so that means that you consider the set of the elements with the fixed norm, yeah, and this so you consider the element with the fixed norm and start acting on them by the group of units, and so you will have orbits. So the claim is that the number of orbits is finite. So this so let me prove it. So prove. So I claim that in each class, yeah. So let us notice that, yeah. So you have this fixed A. So let us form of k divided by A of k. So as we know, is an element of the integer ring. Yeah. So that is a finite set. So finite abelian group. So I claim that in each class modular, so in each class here as the quotient, there exists at most one element up to the multiplication by O of k. So so for each class, there exists at most one element up to multiplication by up to multiplication of psi in the side of k star such that it satisfies this kind of equations, such that norm of k over q of alpha is equal to a. So this yeah, so that means that you have so this thing is a finite group, and of course if you pick up a priori some element in the class, nobody guarantees you that you have this equation that is satisfied, but up to and even up to multiplication, but there will be no more than one class. So let me prove it. So prove the statement. Suppose you have alpha and beta, two elements in the same class. In A times O of k. So this such that the norms are equal. Norm of k of alpha is equal to norm of k q of beta is equal to A. So I claim that we claim that alpha is equal to psi beta for psi belongs to O of k star. And we have, so indeed, so we write down beta as alpha, so from this kind of alpha plus a times gamma, where gamma is integer. And we just, we will divide by alpha and prove that this will be invertible number. Yeah? So we shall write down, yes, we'll let yeah, so yeah, просто, so we write down alpha divided by beta, and this is 1 plus what? Plus a times gamma divided by beta. Yeah? But let us recall that A is a norm of beta. Yeah? So this is 1 plus norm of beta divided by beta times gamma. And notice that O of k, so this is an element of O of k, and the norm of beta divided by beta is also the element of O of k, since you write down the norm of beta, and this is equal to beta. Yeah, so this is a product of all elements over the elements of so which are conjugate, but beta conjugate to beta, so meaning that you apply different different embedding of the field, but one embedding of course is trivial. I mean, when you may think that you start with particular fixed embedding in algebraically closed field, and others are just chosen to be different. And this so the formula for norm looks like sigma 1 sigma n beta. So here n minus 1, yeah, because you have n embeddings, yeah, for our so precisely the degree of the extension, because the extension is separable, and all beta i's, so beta is integer, is on O of k, so the sigma i's of beta are also integer. So the norm of beta divided by beta, which is a product of remaining elements, which correspond to non-trivial embeddings, is also integer. Yeah, and this tells you that the element is integer itself, and but the property is symmetric. Yes, so alpha and beta behave symmetrically. So similarly, if you take from the divide by alpha, so dividing by alpha, we get. And using this that A is the norm of alpha, we get that beta alpha belongs to of K, so these numbers, they are invertible to each other. Yeah? So that means that psi, which is equal to alpha divided by beta, is a unit. Okay. So yeah, so actually the other part will be, so I'm sure that the next part will be lengthy, so I let us move to the next lecture. Because I will be definitely out of time and I won't finish the proof work. But let us, so I shall recall this lemma without the proof, and we shall use it in order to understand how we shall pick up specific set related with this kind of procedure, and we shall also see the translations of this set by O of k, and here you see how it will be worked out. Yeah? So already in this lemma there is an action of O of k. We shall see that translations of this bounded set via O of k will cover the whole space and prove that the group is is of full rank. Yeah? And also, so the remaining part will to notice that the group itself is discrete, so it will be isomorphic to, so generated freely by the corresponding elements. Okay, so thank you.